of Anderson and Klee. Then I spoke about dual varieties. Which were, as I explained, they were, the theory was created exactly 100 years ago, after 200 years ago, after the Napoleon War. But I spoke about things much more recent. It's the conjecture due to Rannestad, Sturmfeld's, and Aboaf. And now I gave the definition of osculating spaces. And I recall that if you have a variety, non-degenerate variety, and a point here, we say that a hyperplane osculates if it is contained in the third, if the local equation is contained in the third power of the maximal idea. So if a hyperplane just passes through X, it's contained in the first power of maximal idea. If it's tangent, it's contained in the second. If it osculates, it's contained in the third, and so on. You can consider high-order osculation. And taking intersection of all osculating hyperplanes, we introduced the osculating space. So this is some linear space which contains the tangent space and there is an obvious bound for the dimension. Certainly it's at least n at a smooth point, because this is contains the tangent variety, and at most the largest possible dimension is like this, because this is the number of quadratic monomials -1, because I consider projective things. So before going further, let me recall some examples that everyone knows. In the case of plane curve, you know that a general tangent lies in tangent line lies in the second power of maximal idea, but not in the third one. But all the curves starting with degree, non-singular curves starting with degree 3 have certain inflection points, and there are finitely many inflection points. So if n is equal to 2 and n is equal to 1, finitely many inflection points. If you take a space curve, then at each point a general plane, tangent plane is contained only in the second power of maximal idea, but there is exactly one plane which has high order contact. It's called osculating plane, and so in a sense all points of this curve are osculating. There exists an osculating plane. But there are finitely many points where this oscillating plane has a higher order contact. And these are very important, and they always exist unless you have a rational normal curve. They are very useful to study curves. And for curves in high-dimensional spaces, particularly important are so-called Weierstrass points, which you also know. They deal with canonical embedding of a curve, and then the highest osculating hyperplanes just meet just osculate at these Weierstrass points. There are finitely many, you know how many, and so on. So just before going any further, let me give some high-dimensional examples which will illustrate the points that I'll make later. So consider a surface in P4 of degree 3, non-singular surface. So this is the blow-up of a plane at one point, or you can say that it's a hyperplane section of the Segre variety P1 cross P2. And so it's a scroll, a ruled surface, which has many fibers and a minimal section L, which is an exceptional curve, as you know. And so the tangent hyperplanes are those that contain some of the fiber. So if you consider the dual variety, and I explained yesterday what is dual variety, it's the variety containing the locus of all tangent hyperplanes, then it will contain a lot of lines corresponding to planes passing to hyperplanes passing through the fibers. So it's a union of the orthogonal complements of this. But there are some special hyperplanes that contain L, and they form a plane pi, which is the orthogonal complement of L, and usually such a plane, such a hyperplane cuts your surface in 3 lines, like this. But this plane contains a conic C, which corresponds to hyperplanes tangent along double line and this minimal section. They form a conic, a one-dimensional family, and to each point of this minimal section corresponds a point in this conic. And you see immediately where you can have and do have oscillations. This is in this point, because here you have double line and here one line, and so you go to the third power of maximal idea. And so the conclusion is that C is the locus of osculating hyperplanes in the dual variety, and this line is the locus of inflectional points of our scroll. In other words, we can say that for x here, for a point x here, the second osculating space is like this. It's either the ambient P4 if x is not in L, and it's P3 if x lies in L. So you see that the dimension can drop. And as I mentioned yesterday, this is a lower, the dimension of this oscillating space is a lower semi-continuous function. And maybe one more example before going to some general results. Consider this Segre product. All examples are very simple. It lies in P7. And the dual variety is a hypersurface. And this is a variety of degree 6. And it's easy to show, it's an exercise, that the only hyperplanes that osculate have the form like this. The corresponding hyperplane sections consists of 3 quadrics. And through each point of this variety x, y, z, they passes the only osculating hyperplane. And these osculating hyperplanes form the same variety in the dual variety, because they correspond to x, y, and z. So you get some P1 cross P1 cross P1 in the dual variety, which forms the locus of osculating hyperplanes. Now this osculating spaces were studied classically, but the recent history, now I make some points about the recent history. Not so maybe recent, for the last 20 years, some of the results. So in 1994, Landsberg published a proof that if you have such a you have a smooth non-degenerate variety, non-degenerate means not contained in a hyperplane, and we know from now on we'll denote the codimension by C. He proved that using the method of moving frames, a highly computational differential geometric method, that if C is small, we have a variety of small codimension, then for a general point, we have this. So there are no hyperplanes osculating at a general point of such variety of small codimension. And this, you see, we saw in two examples of plane curves. And, well, it's not so small codimension, but for a surface of degree 3 in P4, we saw that through a general point there is no osculating hyperplane. Maybe a year ago, my former student Lvovsky sent me some notes where he improved this, but not very much, and he showed that the same is true for this bound. Then I thought a little bit about it, and I made a big improvement. That this is true for C less than equal to n, which is much better. And we saw that, for example, this surface of degree 3 is on the boundary. And this is a big advance, but then I thought about it, and I found and then that actually more or less the same result was known. This I proved by geometric methods, but the same result was proved, equivalent result was proved analytically long ago by Terracini, and then you can consult for it was proved also analytically and differential geometrically in the spirit of the paper by Griffiths and Harris. And finally, the proof with the tribute to Terracini was reproduced in the recent paper by Ionesco and Russo. In American Journal of Mathematics this year. The proof, but this proof is maybe I can say the result in the form that they formulated. They prove actually something stronger, and Terracini proves something stronger. Suppose you have X in some space of arbitrarily high dimension, non-singular X. And suppose that the second variety of X has dimension at most 2n. And this is the same as to say that X can be isomorphically projected to a linear space of dimension at most 2 times n. Then, for a general point X, you have the following. And this is equivalent to our statement. I'll explain what it means. Here, 2 means the second fundamental form. And in plain words, it says the following. Consider an arbitrary tangent hyperplane at X. Then it has some Taylor decomposition which starts with quadrics. And so you obtain a linear system of quadrics in the tangent space parameterized by this variety because PC minus 1 parameterizes all hyperplanes that are tangent at this point. And if it has maximal dimension as here, this means that no hyperplane, for no hyperplane, this form is identically 0. And this, being identically 0, is equivalent to osculating. And so I thought that with it the problem was closed. My result was actually known. But still, this gives us only very little information. And I told about this, I told the story to Christian Peskin. And he attracted some other mathematicians, particularly Laurent Colblain and Gentiana Danila. And they obtained some experimental data. For example, they found that for a hypersurface, so if X is a hypersurface, then there is a smooth hypersurface. There exists only finitely many points where the second osculating space is a hyperplane, which is equivalent to this equality because the tangent space is also a hyperplane. And some other experimental data, and so they made a conjecture, Christian Peskin made a conjecture, which I now formulate. But to formulate it, I need some notation. So I recall that yesterday I introduced the economal variety, which lies in the product and consists of all pairs of a point and a hyperplane such that the hyperplane is tangent at this point. So this is a variety of dimension n minus 1, and it has 2 projections onto X, onto dual variety. This is the definition. Now we consider P2. P2 is a subvariety of P, and it consists of all hyperplanes that osculate. So it's the locus of all points X, of all pairs X alpha, such that this hyperplane contains the second the osculating space at this point. This is no longer an irreducible variety, not necessarily, but still it has dimension and you can study it. And you can consider the two projections, which are just the restrictions of these projections to P2. These are not surjective, of course, now. And so, first of all, I introduce what is called osculation or inflection locus. So, the inflection locus, or I'll soon explain why we'll call it also the first inflection osculation locus, is just the locus of points such that this dimension maybe for the first I just write it in an easy way. We call P2 the image of P2. We call the osculation locus of X, inflection locus of X. That means that in this for points in this O, there exists a hyperplane osculating at such a point, which is not always true, as we saw, for example, for plane curves. For a general point, there is no an osculating line. And now, more generally, we write the case osculation locus is the following: is the set of points of X where the dimension of the inverse image of X satisfies this inequality. Or equivalently, we can write the following: it's the locus of X where the dimension of the osculating space satisfies this inequality. So we obtain a filtration. For a general point of X, the osculating space has some dimension, but for more special points it has a smaller dimension, and so on. And so we have a filtration. So X is equal to O0. Then we get the locus of inflectional point, which is equal to O1, and so on. And finally, we get the last term of this filtration. And now, the conjecture was that the dimension based on experimental evidence, the conjecture was that the dimension of OK doesn't exceed C minus K for all K in these limits. For example, this means that if the osculating space has the same dimension as the tangent space, there are finitely many such points, and so on. So if it's one more, there is at most a curve, and so on until we get to the end. You see that for K equal to n minus 1, we obtain this result of Terracini. But I'll speak about it later. Actually, I proved this conjecture and several equivalent statements. And I'll formulate this theorem now. But before, I'll introduce a similar filtration in the dual variety. If k is equal to 0, then yes, I wrote that we have this equality, trivially. And so here we have the dimension is, sorry, so maybe it's not C, but a priori, but yes, if k is equal to 0, yes, then you get that the dimension is less than codimensioned. And so this implies that n capital is greater than 2n. But okay, let it be 1. So we introduce a similar filtration in the dual variety. And first of all, we have Q2. This is the locus of all osculating hyperplanes. So we have O of x star which is also or 0 of x star. No, it's sorry, x star is equal to O0, and the osculating subset is equal to O1, and it's just the image of Q2. And we introduce OK, OM, of x star as the locus of all alpha, such that we have this inequality. What does it mean, this inequality? It means that we consider the hyperplane which oscillate along a subvariety of rather big dimension. You can have either this inverse image can be empty and then this hyperplane does not oscillate at all, or it can oscillate at a point as here, or it can oscillate along a curve and so on. And in this way we get a filtration, descending filtration, I'll explain why we stop in a few minutes. I'll explain why we stop here. And so I formulate now I formulate a theorem. The following claims are equivalent and true. So first, so you see three statements which are all very easy and which describe, on the one hand, they give a bound for the dimension of subvariety of inflectional points. On the other hand, they give a bound for the dimension of hyperplane that oscillates along something very positive dimensional. And on the third hand, they give a bound for the dimension of this variety, which is an analog of conormal variety. And actually, the proof used that I gave used also a theorem of tangencies that I will need later, and so I formulated it, and it gave some properties of for the cases when we are on the boundary. So in particular, and if we have, for example, in 2, if we have an inequality, from this it follows that the oscillation is along a linear space, that Q2 minus 1 for a general point alpha, this is a linear space of dimension m minus 1 if alpha is here general. Now maybe I'll recall theorem on tangencies because we'll need it soon, and it also explains why we stop here at C, because a priori we could have longer filtration. So suppose that we have an undegenerate variety X, which is smooth along a subvariety of dimension m, and we denote by T yx a union of tangent spaces to X along Y. So it's and we denote by SYX the join of Y and X. That means that we consider all lines joining points of Y with points of X, and their locus is called the join or the relative secant variety. And the theorem says that, in the first formulation, the theorem says that either these two varieties are equal, or we know their dimensions, and they are the following. Maximal possible, because you see these are the expected dimension, because Y is m-dimensional, X is n-dimensional, and so the largest possible dimension of this family is m plus n. And here, for the join, we have one dimension along Y, m dimensions along Y, n dimensions along X, and one dimension for the line. And so these are the maximal possible dimensions. And as a consequence, we get the following theorem, which is usually called the theorem on tangencies. Suppose that you have a subspace L in Pn of dimension R. Suppose that it's tangent to X along Y. Then R is satisfies this inequality. And the proof is as follows, What does it mean that L is tangent to X along Y? That means that L contains this. Contains all hyperplane, all spaces tangent to X at the points of Y. Can we have, and we have an alternative, can we have the first case here? The answer is no, because X is not contained in L, because it's non-degenerate. And so we can have the first alternative. Therefore, we have the second alternative. And since L contains this, and this has dimension m plus 1, m plus n, then the dimension of L is at least this. In other words, an r-dimensional space cannot be tangent along a subvariety of dimension greater than this. And we can say something on the case of the boundary. And this explains why we have linear spaces here. Okay, maybe I give two corollaries of this theorem, of this, where is the theorem? Here. Which explain how it can be used. First, we consider the case when X is a general point in the above notation. Then we can bound the dimension of the osculating space, and it's always I have to write this because if your variety is contained in a projective space of small dimensions, then of course this number is small, and this means that you don't have osculating spaces at all, only the ambient space is osculating. But this is the meaningful part of it. So, and this follows immediately from claim 1 of the theorem, because it shows one implies that for you have the following. I just rewrite it a little bit. And so from this you immediately get this. So the maximal, if you have a non-singular variety, then the osculating space cannot have, at a general point, cannot have a dimension less than 2 times the dimension of the variety. And by the way, this of course implies this result about which I spoke, the result of several people, but which was finally it came back to Terracini. Because if the minimal possible dimension of osculating space is 2n, then your variety cannot lie in a linear space of dimension less than that. Otherwise, the osculating space will coincide with the ambient space. But this is not all, because it's very interesting to understand for which varieties you have an equality. And this is an interesting problem which is completely unsolved. One example is given by Scrolls, examples for which a general osculating space has dimension 2n. The first example, and this is a very easy exercise, are scrolls over a curve. So suppose you have a map to a curve whose fibers are linear. Then it's very easy to see that they give an example of such varieties. But even for surfaces, there are dozens of papers and many recent papers which try to classify the varieties for which you have equality here. And the first examples were given by Togliatti classically, and now there may be around 5 different examples of surfaces for which you have an equality here, and this is a very interesting problem to understand their classification. Although this result gives some insight that special hyperplanes oscillate along a line, for example, for surface. And other things which were studied for surfaces is when you have everywhere number the dimension is 4, or sometimes it can drop. It can be 3 at certain points. And it's always 4 only for scrolls of special type, which are product of a line and a curve, really product. But for high dimensions, one knows almost nothing. This result can be extended and for high osculating spaces, and then you replace here 2 by the order of oscillation. And again, scrolls give the example on the boundary, but what are the other examples? This is not known. Okay, maybe I write as another corollary, which I already mentioned. For k equal to c, you get the locus of points where you have this equality. Is at most finite. So we saw this in the trivial example of plane curve. For any hypersurface, I already mentioned that there are only finitely many points where exist oscillating hyperplanes, but this is true always. And the intermediate cases, I also explained that if you have your oscillating space is of dimension n+1, then there is at most a curve of such points. And so you, starting with any variety, you get an interesting structure. You get some filtration, which is meaningful geometrically and might play a similar role, say, for canonical embedding as Weierstrass points play in the theory of curves. For example, you know that Weierstrass points are used to bound the number of automorphism of a curve. So maybe you can do this in general. But this is not the end of the story. So we came here. What comes next? Next, I communicated to Peskin the proof of his conjecture. And he studied the proof and said, but you proved a much more general thing. And here we return to the notion that I introduced here. Although we only later realized that this has something to do with the problems that we were studying. So definition. I modified the definition I gave yesterday. Let X be an arbitrary variety and take a point in the dual variety. This point is called A singular. If it satisfies this bound. So here must give some explanation. I recall that yesterday we just put this angular brackets without t. Now what is t? T, as I already introduced this notation, is the following. You take a point alpha in the dual variety, you consider the tangency locus of it, the points at which this hyperplane is tangent on our variety. This is some scheme. I recall that it need not be reduced at all. And then you take the union of the tangent spaces to this scheme. And this is always defined, as you know, the notion of the Zariski tangent space is defined for any scheme. And so we introduce this notion of asingularity. And this is more restrictive because if you take the linear span of the entire, say, nilpotent scheme, then you get a linear space of dimension a priori much more. And here you cut only with this infinitesimal neighborhood of order 2. Okay, and now we denote the locus of asingular points as before, but without letter index W, which corresponded to weak. Now, it turned out that my proof actually proved the following theorem. So I can say Fyodor Zak. The dimension of this satisfies this inequality, is bounded by the following. And more precisely, if you take a general point alpha in this variety, general, then we can say something about the tangent space. To this subvariety of dual variety at this point, it's orthogonal to this variety that was used in the statement. To the span of tangents to the variety of contact. And this can be viewed as a foregoing generalization of reflexivity theorem, if you think about it. And actually we think that it is the orthogonal complement, but this we cannot yet show, which means that it coincides with orthogonal complement. Now, I should give some explanation why it implies this result on osculation first, and then give some examples, because there are numerous examples of application of this theorem, orthogonality theorem. And you see that this is just the right way to generalize this theorem of Anderson and Klee, because the result is virtually the same, but the object is different than was used in the previous conjecture. So, why this can be applied to the case of osculation? The answer is as following. Suppose that you have this hyperplane alpha, and which osculates along some variety, subvariety, let's call it y. It's this inverse image. And what does it mean that it osculates? If you think about it, of course, and we should study this inverse image. If you think about it, you see that osculation means that this inverse image has really nilpotence, and actually it contains all the tangent spaces. If some hyperplane osculates at some points, that means that it really contains not only the inverse image contains not only the point, but the point with the first with this second neighborhood, infinitesimal, by the very definition. And then you have you can prove the second assertion of this theory that I formulated, because you know you can apply the theorem of tangencies, and from this you get by the theorem of tangencies you get this inequality. And this is precisely C minus M. So this implies the result for oscillations that I told you about. But even without this application, there are lots of other applications. Let me show even on the simplest example that some very trivial questions, very elementary questions about even curves or surfaces were not known. Take for plane curves, of course, we get nothing because not enough freedom. But take even a space curve, and we can ask some questions. For example, suppose we are interested in the planes here. In the planes, the dual curve lies in the dual space, and we take. We are interested, suppose, in the planes which are tangent to C at 3 points, 3 distinct points. Suppose, of course, you can construct a lot of such curves, but suppose there are sufficiently many of them. So let tau be the subset of the dual subvariety of dual variety. Such that if we take a point in this subvariety, which is a curve, we assume that this is a curve. This is a surface, so many means being a curve. Suppose that the hyperplanes, the planes from here are tangent to C at least 3 distinct points, generally. What does this theorem says? What does the theorem say? It says that this point should be aligned. So if there are infinitely many planes tangent to a space curve, at least 3 points, then all the points of tangency should be aligned, should lie on a line, because you know that this tangent space to this is orthogonal to the plane or to this subspace spanned by these 3 or more points. And if it is one-dimensional, therefore this linear span has only to be also to be one-dimensional. And so this shows that the tangency points are aligned. Now, can we give an example of such varieties, of such curves? Yes, of course. Take some cone over a curve in P2 and intersect it, say, with some surface in P3. Then we obtain a smooth curve, and depending on the degree, if the degree of this surface is d, then all this tangency spaces, the plane which is tangent to the cone at any of these points is tangent to the curve at all these points, clearly, because the tangent plane to the cone doesn't vary along this line. All the planes are the same. It's not clear? Take any cone over a curve anywhere, or not necessarily over a curve. Then I say that these points are smooth. The only singular point is here. And the tangent plane does not change when we move this point along the generator of the cone. Because it's clear, it's spanned by the tangent space to the base of the cone and the vertex. And so if we now intersect this cone by some hypersurface, in our case a surface, and consider this hyperplane tangent to the cone, then it will be tangent to the curve in all these points, because the tangent space to the curve is contained here. And so we get an example where the tangent planes are tangent at many points, and we see that here they are aligned as predicted by this theorem. And what we can easily show that this is the only case for non-singular curve in P3. So all curves are obtained in this way. But then you can put a lot of such questions, and each of them admits a solution, and you can give them to a student each problem. For example, take a hypersurface even. And consider the hyperplanes which are tangent at the same 3 points. So we consider again this subvariety, and suppose that it has dimension n minus 2, as in this example, n minus 2. Then the tangent at least 3 points. Then you can probably describe all these hypersurfaces, and you know by the theorem that the tangency points are again aligned. And you can formulate a lot of other equations like this. For example, consider a surface in P5, smooth. And suppose that there exists a one-dimensional family of P3s tangent along a plane curve. Describe all such surfaces. So why, for example, plane curve? Because as long as we know the dimension of the linear span of the tangency locus, we can compute the dimension. And if it's extremal, probably you can give a classification. So you have a lot of even very easily formulated problems to which there were no answer, but now there is. And I'm sure that this theorem will have a lot of other applications, and it gives you an understanding really of the singularities of the dual varieties. It has a lot of strata, and each of them seems to have the same property as the dual variety, which generalize this reflexivity property, which is very important, not even only in mathematics, but in mechanics. It started in mechanics. It was the duality between Hamiltonian and Lagrangian formalism that is revealed by this duality. And I hope that it will bring many more more new results and new theorems. So thank you.